What's up, Algebra Bros and Broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get studying! Hey, and welcome. Today we're going to talk about our upcoming Exam 3. Exam 3, our third exam, and you've been getting my emails, you know what's going on, but this exam is going to be on Monday, May 3rd, during our class lecture time. You got it. But let's talk a little bit about the content and some logistics. Let's start with the logistics. We're sort of talking about that anyways. No calculators. Hey, I'll just say right now, no calculators. If you got a calculator, throw it out the window. Don't bring the calculator in. Make sure you have your student ID. Got it. Show up early. We'll go through all the we've done this before. You know what we're doing. You've done it, hundreds of times, thousands of times, millions of times. So same old, same old. What is it going to cover? Well, it's going to cover our material from chapters 5 and 6. Let's talk about what chapters 5 and 6 are going to have for us. Let's get a fresh new page. What are the sections that we have? We have 5.1. What was that on? That was on eigenvectors and eigenvalues. We'll go back through and we'll talk about these a bit more. And there was 5.2 on the characteristic equation. Get out of here. 5.3 on diagonalization. 5.4 on eigenvectors with linear transformations. And then that brought us to chapter 6. We had section 6.1 with dot products. 6.2 with orthogonal sets. 6.3 with orthogonal projections. We had 6.4 with the Gram-Schmidt process. And lastly, we had 6.5 with our least squares problems. Let's go back through. Let's, try to do a recap here on what we were talking about in each of the sections. 5.1 and 5.2 really tie together perfectly. It's our introduction to eigenvectors and eigenvalues for the course. 5.1 in particular, we talked about what it meant to be an eigenvector, what it meant to be an eigenvalue. So remember, we have A times some non-trivial vector v is equal to lambda, a scalar, times that vector v. Then that non-trivial vector v is considered an eigenvector, and lambda, the constant lambda, is the corresponding eigenvalue. So we're saying, okay, some matrix times a non-trivial vector produces just a scaled version of that vector back out, and we're talking about eigenvectors and eigenvalues. We went through a lot of examples, we really built that strong foundation for it. But then in section 5.2, we wanted to start talking about, well, what if I wasn't verifying that something that I was given is an eigenvector or an eigenvalue? What if I just have a matrix, and I want to find the eigenvalues and then the corresponding eigenvectors of that matrix? That's what we talked about in 5.2. Remember, the characteristic equation comes from setting that determinant of A minus lambda I equal to 0 and solving that. And so when we find that determinant of a minus lambda I, that gives us what's known as the characteristic polynomial. Setting that characteristic polynomial equal to 0 and solving is what we refer to as the characteristic equation in its entirety. And from that method, remember, we're finding eigenvalues. Once we have the eigenvalues, we can then go and find the eigenvectors, and everything works out really nicely from there. Okay, well, so then what's the motivation to doing this? Well, one of those motivations is diagonalizing matrices. So then in the next section, 5.3, we talked about how we can diagonalize matrix A and write A as similar to a diagonal matrix where A is equal to PDP inverse, where P is an invertible matrix and D is a diagonal matrix. And we talked about all the steps here, so make sure you know how to diagonalize a matrix, make sure you're comfortable with that process, make sure that all of this feels good. And then 5.4, we saw a lot of really cool examples working with linear transformations, talking about tying in information from diagonalization into linear transformations. A lot of cool diagrams too in the lecture video talking about how we can sort of view these things and what it is we're really talking about when thinking about these linear transformations. But aside from that, we had a lot of cool examples. I'm going to say make sure you study those cool examples that we had. You know, I can't really do a full recap of this, but luckily we got those videos up. Go back and look at 5.4 and make sure you're comfortable with all those cool examples we talked about trying to bring linear transformations back into play. Chapter 6, definitely a favorite. Let me know in the comment section below if you prefer Chapter 5 or Chapter 6. I know a lot of you were loving the material in Chapter 6, and I can't blame you. In 6.1, we had a really nice introduction to the chapter, talking about inner products, dot products, talking about unit vectors as well in the section. Really going through and building a strong foundation, really seeing a lot of arithmetic examples. And then at the end, we got the chance to talk about WPERP. I know you love WPERP. And we talked about those orthogonal subspaces, which was really, really cool. Which brought us to 6.2. And 6.2 kind of runs into 6.3. I really try to group these two together mentally. We took a look at what it meant for a set of vectors to be orthogonal, checking to make sure that the dot product gives us is the scalar 0, to make sure that two vectors are orthogonal meaning perpendicular. And we started introducing the idea of projections, orthogonal projections, which carried into 6.3. And in 6.3, we really went a lot further with it. We showed a lot of nice results in both of these sections, but in 6.3, we started talking about orthogonal projections a lot more and how we can write a vector y as the sum of two vectors, the projection vector y hat, plus some other vector z, where these two vectors are orthogonal to each other. Right? So these two vectors are orthogonal to each other. We get this really nice decomposition from our orthogonal decomposition theorem. So a lot of really cool stuff in there. We also talked about the best approximation theorem. My favorite theorems. Really showcased that result as well, showing a derivation of it. And moving forward with orthogonal projections, we went to 6.4. We talked about the Gram-Schmidt process, which is really fantastic, very amazing. I know you've all been loving the Gram-Schmidt process. Let's talk about why we're loving it so much. Is that we were able to start with some basis, and not an orthogonal basis necessarily, just any basis. Vectors call them x1, x2, x3, and then so on and so forth. Let me just stop there. What Gram-Schmidt process allowed us to do was to take this non-orthogonal basis and to go through this algorithmic process to transform this into a new basis where the vectors are now orthogonal. We call those vectors, v sub 1, v sub 2, v sub 3. Remember, we got that first vector v sub 1 for free because one vector by itself in a set is not necessarily orthogonal or not. It really needs another vector to compare it to. It's that sort of comparison that I'm looking for. But what was really special about this is that when I'm going through the Gram-Schmidt process, span is preserved and not altered. The span of the sets is preserved, and that's amazing because we're not really losing out on anything. We're gaining all of those nice properties of having orthogonal vectors. And this happens line by line, play by play, as we build this new basis. So as I'm just building this first vector, if I were to think about the sets just with their first vectors only, span is preserved. But then as I'm working with a set of 2 vectors and building my 2 vectors, the span is still preserved. And then when I move on to that third vector, the span is still preserved. So every line, every step along the way, we are preserving span. And we're now getting this orthogonal basis to work with, which is wonderful. We took a look at an application of this working with QR factorization, right? And we're going to see more need to have orthogonal vectors, orthogonal columns, things like that later on in the course too. And then my favorite, the last section that we looked at in chapter 6, least squares problems. And remember, we had the normal equations that we were working with. We had A transpose A times X hat is equal to A transpose B. And we solved this as an augmented system, right? So A transpose A was our coefficient matrix. We then would solve for X hat by augmenting this with the column vector given by A transpose B and solving. There was also a way that we could solve directly using inverses, but you remember that I mentioned in the video that I really want you to just focus on the normal equations. That's really the way to go. But we did also say that, hey, if you think of A transpose A as just one matrix, if it's invertible, you can multiply both sides by the inverse and have a direct computation to solving using inverses. But we said, nah, let's use the normal equations. We love the normal equations. It's our favorite. And we also took a look at how the least squares problems translate if I happen to have an orthogonal set of column vectors. However, that's very important to keep in mind that when we were using the normal equations and working through that, A wasn't necessarily set up as a matrix to have those orthogonal columns. So it's sort of 2 separate ideas in the same section that I want you to definitely keep sort of separate. Make sure you're comfortable with what those 2 types of problems were and how to tell the difference between them as well. But hey, that's what we're looking at. Not a ton of stuff, but definitely a good group of material to be covering between chapters 5 and chapter 6. Remember, it's never too late to start studying. Let me just jot down an idea here. Whoop. Never too late to start studying. But in saying this, I want to also point out that, hey, it's never too early, right? Am I right? To start studying. So good luck, and as you're studying, let me know, right? Reach out to me, leave me a message, send me an email, let me know what you're studying. If it's going well, give me a thumbs up. If it's not going well, let me know what I can do to help out. Let's try to make sure that everything's feeling good for the upcoming exam. I hope you're doing great. Hey, if you're feeling a little bit stressed out, I get it. It can be a stressful time of the semester. But let's just remember to relax. And we've been working on those deep breathing exercises too in the previous videos. Make sure that you're keeping up with those. To calm down, get a nice warm glass of tea is really good, like a mug of tea. Or let me know what you're drinking. If you're drinking tea or coffee or soft drinks or something like that, let me know in the comment section below what you're drinking in order to, get yourself relaxed, but also kind of hyped a little bit for this exam. I think you're really going to enjoy it. And hey, remember, you're the best. You can definitely do this. You're going to get a perfect score. don't forget, you know where to find me if you need me. Let me know what I can do to help you. But hey, looking forward to it. You know, no matter where you are and what you're doing, remember to always keep studying, keep dreaming, and follow your heart. And I will see you for the exam. Until then, take care. You totally got this.